Okay, so welcome back. Last time we saw the definition of an inner product, okay, and a norm of a vector. Okay, so I won't go through the whole definition, but you should think it's a function that inputted two values, two vectors, outputted a real number, okay, or complex number, depending on what field you're working over. And roughly it takes into account the angle between the vectors and their length. Okay, so this is kind of the if you want to compute the inner product, this will be the information that you need. All right, so here's definition that we've seen before in a very specific context of a specific inner product. General, you say that two vectors are orthogonal. Okay, and I'll write v perpendicular w if the inner product of v and w is 0. Similarly, two subspaces are orthogonal. Okay, if the inner product of v and w is equal to 0, say for all v in one subspace and for all w in the other subspace. Okay, so a standard picture would be something like the xy plane is orthogonal to the z-axis in using the standard inner product, okay, on R3. XY plane is orthogonal to z-axis. Okay, so the first thing to prove about orthogonal vectors is, and this is straightforward computation, if v is perpendicular to w, then it satisfies Pythagorean's theorem. Okay, so the norm squared of v plus w is the norm squared of v plus the norm squared of w. Okay, so this is Pythagoras. Okay, so this is quite easy. You just write this as v plus w, the inner product of v plus w with itself. Multiply it out using linearity, and the two cross terms are equal to 0 because orthogonality. Okay? You can actually do this more generally. So more generally, if vi, I'll just say I equals 1 to k, is a collection of vectors, okay, and vi is perpendicular to vj for all ij, okay, then if I take any linear combination, so I equals 1 to k, alpha I v sub I squared, then again, this is just equal to the sum of the alpha I squared times the norm of the v sub i's. Okay, so norms of elements are quite easy to compute as long as they're sums of orthogonal vectors. I'll say such vi are usually called orthogonal systems. We'll be most interested when the vi form a basis. Okay, so if the vi as above are a basis, then it's an orthogonal basis. Best example is, of course, the standard coordinate vectors in Rn. Okay, and also what those also satisfy is if you have such a vi, okay, are a basis, and the norm of vi squared is equal to 1 for all I, it's an orthonormal basis. Okay, so an orthonormal basis is a basis, all the vectors are orthogonal, and they all have length 1, i.e. it looks very much like the standard coordinate vectors in Rn. Now, Here, then, the formula is very easy to compute, right? Because all of the, not only do all the cross terms are 0, but also this is just equal to 1 for all I, okay? And you kind of recover this distance formula that we saw last time, which was the norm of v, or norm of x1 up through xn in Rn, right? It was just equal to the square root of x1 squared up through xn squared, okay? This is just what this formula is saying, and it's just using the fact that we have an orthonormal basis for Rn that we're writing these coordinates in. Okay, so let me just record another lemma, which we saw earlier. I'll sketch the proof. If vi from I equals 1 to k is an orthogonal system, okay, then the v sub I are linearly independent. Okay. So this is not too hard to show. So suppose that you can write, let's just say you can write v sub k as a non-trivial linear combination of the other ones. Okay, so I'm writing up to v sub alpha k minus 1, v sub k minus 1. Of course, you're doing this for a specific vector. It doesn't really matter which one you're doing. So suppose you can write this linear combination, okay? Well then, what we know is that if I look at vk, alpha 1, v1, up through alpha k minus 1, vk minus 1, this will be greater than 0. Because this is just the inner product of vk with itself, which is greater than 0 if vk is non-zero. On the other hand, all of these individual terms are orthogonal to the vk, so by orthogonality it would have to be equal to 0, and that's a contradiction. Okay? So that's really all there is to it. Okay, and this gives you kind of an upper bound if you have a finite dimensional vector space. Well, it tells you that you shouldn't be able to keep finding vectors that are orthogonal to each other, right? Eventually you run out of room, and then you should hopefully get an orthogonal or orthonormal basis. Okay, so let's work with an orthonormal basis for a second, because it turns out these are kind of nice to work with. Okay, so I'll call this vi from I equals 1 to n now. Okay, so let's write x in v, okay, as a sum, alpha 1 v sub 1 up through alpha n v sub n. Now, if you have an orthonormal basis, it turns out that these alpha I come up quite naturally, okay? So the coordinates of any vector happen to just be the inner product of x with the ith basis vector. Now this is easy to see. I mean, in particular, if you take alpha 1 v1, so this is my x, alpha n v sub n, here's v sub I. Well, again, by linearity, the only thing that you detect, I mean, because if j is not equal to I, all of these cross terms will be 0. So you only pick up alpha I times the inner product of vi with itself, and since this is 1, you just get vi. Okay? So in particular, what you obtain is that x is equal to the sum of x with respect inner product of x and vi. So for the standard basis in Rn, this is probably something you just do without thinking about when you're computing the coordinates. You're really computing the inner product of the vector with these standard basis vectors. And the power of this formula is that it works in general for any orthogonal basis. If you want to find the coordinates of a vector, you have to compute the inner product. And sometimes it's easier to compute this inner product than to actually find the coordinates. So let me give you just the briefest sketch of an interesting example. Okay, so you can look at functions, say, on an interval, which is easier to do like from negative pi to pi, okay, with an inner product equal to 1 over pi. This is just something to make the functions a little nicer, or the constants. Negative pi to pi, f of x, g of x, dx. Okay, so it's an inner product we saw before. I have to be careful about what functions I'm looking at. I'm not going to really think about that now. Okay, and if you want to think about continuous functions, that's perfectly acceptable. Now it turns out, if I put in my numbers correctly, that cosine of nx, okay, for n in n, and sine of mx for m in n are an orthogonal basis. Okay, I'll just say an orthogonal system. Be a little bit more careful in what functions to include if you want to say that they span the set of functions. Okay, so you should think that you can check this just by various integral computations, right? So you're integrating sine of mx times cosine of mx, you're integrating cosine of mx times cosine of nx, and for various m and n, okay? And then computing the integral of cosine squared. So in general, then you can write, oh, and I guess I should have a constant in here as well. That's also important. And then I can write a general function as a constant plus the sum from n equals 1 to infinity of an cosine of nx plus the sum from n equals 1 to infinity of bn sine of n. Oh, I'll just say m sine of mx. Okay? So it turns out this is just writing a function in terms of its basis. Okay? And the good news is now that the an and the bm are not too hard to compute. Right? And you can imagine now you have this basis, but you might have a very explicit formula for the function, and that's, going to be hard to determine the exact values. On the other hand, since they're orthonormal, all you have to do is integrate that function times cosine or that function times sine. Okay? And that, if you want a computer to estimate the Fourier, so this is called Fourier series, if you want to have a computer estimate the Fourier coefficients, it can do this quite easily. Okay, so let me go to the next kind of important thing that you can do with using this concept of orthogonality. Okay, so there's orthogonal projection to a subspace. Okay, so what is this? Given, say, V in V, W contained in V a vector subspace, then pi sub W of V, so pi is a map, you can think of it just going from V to V, pi W of V is in W, and they're orthogonal. So if I look at V minus pi W of V, or pi minus, is orthogonal to W. Okay? So the picture is we have our V, we have our W sitting inside. Take any vector. This is pi project to W, so this is pi W of V. Okay? And the key is that the difference is orthogonal to this subspace. Okay? So if you saw a plane, it would be a similar picture. You take a vector. Here's the projection, and it's orthogonal to any vector in that plane. Okay? So you have to check that this exists. So claim this is a unique linear transformation which does this. Okay, so it takes a little bit of work to show it exists. Okay, but let me just say how you would construct it. To construct it, well, you would need, so first you need, and I'm just going to stick to orthonormal just because it makes every formula easier. And it's also easy to see, if you have an orthogonal basis, then you can have an orthonormal basis just by multiplying by constants. So we need an orthonormal basis for W. Okay, so suppose we have that, W1 up through wk, then where do you send v? So pi w of v is exactly going to be the inner product of v with the wi. Sorry, so this should be a sum from I equals 1 to k, v sub wi, wi. Okay, so the first hint that this is kind of the right formula is that you should note it fixes all vectors in W, right? So notice the orthogonal projection should just send pi of, so I'll just say pi of W to W prime is W prime, okay? And that's because we had worked out this formula if you had an orthonormal basis previously, okay? So if you're in W, these are your coordinates and it just sends you to your coordinates. In general, if you have a vector v, it sends you somewhere else. Also notice that if v is orthogonal to w, then of course this goes to 0. Okay, then pi w of v is 0, as it should be. Okay, you want, if you're an orthogonal vector, so here this vector v was here, if you were actually orthogonal, you should get sent to 0. Okay, so let me do just an example of this standard picture in R2. Okay, so this will be the diagonal subspace. An orthogonal vector here, sorry, an orthonormal vector here is just 1 over square root of 2, 1 over square root of 2, right? This has norm 1, okay? If you want to see where, say, 1, 0 goes, then you would take its inner product with 1 square root of 2, so you get that it goes to, which is 1 square root of 2, right? That's the inner product of these two vectors. So you're getting that it goes to 1 over root 2 times this vector, right? That's your basis. So you get that it goes to a half, okay? Which we would have known since the orthogonal projection is going to take it to the center of that square, okay? Same thing for 0, 1, and that determines the linear transformation completely, okay? So to see that this is, the right formula is just a computation, okay? So the only thing to check is that if you take v and you look at its image, okay, which is minus vi from I equals 1 to k, you have to just check that this is orthogonal to vj for all j, okay, and therefore it will be orthogonal to the subspace, and that's what you'd like, okay? And this is, well, if you just, again, write this out, what you're looking at is vj, okay? And then again, these are orthogonal, so basically everything goes to 0 except for vj, okay? And this is 1, so you get 0. Okay, so to check uniqueness, okay, and also to see that, and this is also just an important property of orthogonal projection, if you take v minus pi w of v, okay, the claim is that this is less than or equal to the norm of v minus w, for all w and w, okay? So in other words, if you take this projection and you look at a vector, you are projecting to the closest point. This orthogonal projection is projection to the closest point on W. Okay? So let me take V, pi W of V. Here's some other W prime. We want to show that this length L prime is bigger than this length L. Okay. Well, now we can write V minus W prime. This is V minus the projection plus the projection minus w prime. Okay, so I'm just writing this vector that we're interested in as this vector plus this vector. On the other hand, these two are orthogonal. Okay, so the norm of v minus w prime squared by Pythagorean theorem is v minus pi w of v squared plus pi w of v minus w prime squared. Okay, so therefore this error term or this sum shows you that this is always greater than or equal to this. Okay, so the orthogonal projection, since it's an orthogonal decomposition, you get this, and therefore it's the kind of distance minimizing transformation, which takes every vector in V to a vector in W. Okay, so unfortunately we still haven't shown that it exists, right? We've only shown that it exists if you have an orthonormal basis. So what we would like is a way to convert any basis into an orthonormal basis. Okay, so this is called Schmidt. Usually it converts orthogonal into an orthogonal basis, but you know, it's easy to make it orthonormal, so I will, okay, because the formulas are nicer. Unfortunately, it means the formulas here are going to be slightly nastier, but that's okay. All right, so what does this do? So it takes V1 up through Vn. It converts it to W1 up through Wn orthonormal. Okay, and slightly better, or even stronger, if I look at the span of V1 up through Vk, I get W1, it's the span of W1 up through Wk. Okay, so let me just draw the picture. So I take any random basis, you know, V1, V2, V3, and I somehow want to produce an orthonormal basis out of this. Okay, so this is done inductively. Okay, so it's an inductive procedure. So how do I define W1? Well, it should be in the span of W1 should be the span of V1 by this condition. So I just have to make sure that V1 is unit norm. And now there's a nice trick here, which is you just set it to be V1 over the norm of V1. Okay? And obviously when you take the norm of this, notice this is just a rescaling so that this has norm 1. Okay? So W1 is, say, here. Okay, so that's a nice little trick to know. So now what do I do with W2? Okay? Well, I notice that I better start with V2 in some sense, right? Because I want the span of W1, W2 to be the span of V1, V2. W1 is just a multiple of V1, and I want the spans to be the same, so it should be in the plane spanned by V1 and V2. Okay? Well, now what do I do? Well, now I know how to define, orthogonal projection to, say, the span of V1, right? So I found my W1, my orthonormal vector, so I know the formula for this projection, okay? I could have done the same with orthogonal and just, you end up compensating for this in the definition of the projection, but you can do it here, okay? So now, what do I want to do? Well, it should be I want it to be orthogonal, so I should just take its V2 minus the orthogonal projection onto span of V1, V2. Okay? Now this is good in the sense that it's orthogonal to V1 by construction, right? It's bad because it no longer has norm 1. On the other hand, this is easily fixed. I do exactly the same trick as before, and so this is a vector, and I'm just going to divide by the scalar norm of whatever it is, norm of W2. Okay? So you can check, I mean, the only thing you have to worry about is whether you're dividing by 0, but the only way that this could be is if v2 is in the span of v1, and that's not going to be true by assumption. Okay, so now I have an so now I think we can see how the inductive procedure works. Now I get an orthonormal basis for for the span of W1 and W2, which is the same as the span of V1 and V2. Okay, now rinse and repeat. I want to take W3. I'm looking at V3 minus the projection onto this span. Okay, I have an orthogonal basis. I know what to do. And again, you divide by the norm of W3. Okay, so I know that this, formula doesn't make sense in the sense that I'm defining W3 in terms of itself, but you just stick that in for there and it all makes sense. Okay, and that works. So this is exactly how you do it. You essentially take every vector in VI and inductively project onto the orthogonally project onto the subspace spanned by the V1 up through V sub I minus 1. Okay, so that's it. Again, you could take, there are formulas, you can check them all. The book certainly has them, but it's almost better to just have this picture of orthogonally projecting without actually, ever writing down the formulas. Of course, sometimes you actually need to compute what these bases are, and then you better work out these, then you do have to work with the formulas. But if you're just kind of thinking of applications of Gram-Schmidt, it's easier to just have this picture in mind. Okay, so as an application of this, let me give you something similar to what I defined before for Fourier transformations, but now we're only going to be dealing with polynomials. So it's somehow more elementary, though there still has a lot of applications. Okay, so they come from an inner product, so there's an inner product on the space of polynomials, come from an inner product on Pn. Okay, so polynomials, I mean, you can also do this for just all polynomials of arbitrary degree. Okay, and it's what we've seen before, okay, in some sense. So it's -1 to 1 f of x g of x dx. Okay, so this is the inner product of f and g. Now notice this is not kind of the usual inner product that you get from the standard basis, okay, that you get from, 1 t squared and so on. So you can do that, so you can, that's certainly a fine basis that you can work with. On the other hand, this tells you, more or other interesting information about what your polynomials are doing, right? So here, for example, t would be orthogonal to t squared, like if this was the standard basis, standard inner product. And here it's clearly, oh no, I think I chose one where it was. Okay, sorry. So t squared and t to the fourth are orthogonal with the standard inner product and are not orthogonal here. Okay, and now if I want to get an orthogonal basis here, well, I can just apply the usual process to the standard basis that I have for polynomials. Okay, so the first one, well, you apply 1. The norm of this is 2. So the first polynomial here, Lagrange 1, is equal to 1 over root 2. Okay, and this, a lot of people would write just 1 here. They normalize in a different way. Okay, the important thing is it's a constant. Okay, and then you figure out what the constant should be. Okay, so what's the second one? Well, you apply t to this Gram-Schmidt process. Okay, so what you get is t, oh, and I think I'm switching from t to x, sorry, so I have t going from minus the inner product of t with 1, okay, so 1 over root 2t times, so this is dt, times 1, okay, so this is the inner product times the vector, and here we're lucky, this just goes to 0, okay, so we just get t, and then we have to remember that the integral from -1 to 1 of t squared is 2/3, okay? You want to divide by that norm, so you get t, I think, times square root of 3/2. If I did that correctly, you should integrate it to get 1, which I think you do, okay? Or integrate, this squared to 1. L3, you just start doing the same thing. So you can, you take t squared minus its projection here, so you get the inner product from -1 to 1 of t cubed 3/2. This times the vector t 3/2, okay? Plus, minus, now the inner product with L1, so you get -1 to 1 t squared 1 over root 2 times 1 over root 2, okay? Again, this kind of looks nasty, but a lot of these cancel because are just 0 because you're integrating an odd function here, okay? Anyways, you'll end up here with 3t squared minus 1 times square root of 5/8, and the procedure just, continues, okay? So again, from this kind of knowing a standard basis for polynomials and a kind of weird inner product gives you these interesting orthogonal vectors, okay? And again, these are, if you Google search, you'll just find them all over the place. Though quite likely with different coefficients, as this inner product usually has a different constant term here. Okay, so let me jump to another application of this, or really an application of the orthogonal projection. Okay, so really the application is that, we now know how to compute the smallest distance between a vector in a vector space and a subspace, okay? So now, well, we can, start with a linear equation, okay? And we've, done a lot of work in this course to give conditions on, say, if we have a transformation A, the conditions on B, so that B is in the image of A. So now, well, the question is if B is not in the image of A, so this, this linear transformation or the system of linear equations does not have a solution, what do we do? Well, we can try to minimize the error. Okay, so in other words, we want to find x so that the norm of ax minus b is as small as possible. Okay, so I'll just say is smallest. Okay, and now we know what to do. Okay, so this x is precisely the orthogonal projection of B to the image of A, okay? So in other words, x is a solution to this equation. Ax is equal to orthogonal projection onto the image of A of B, okay? And now we have, formulas for this vector, okay, so we can now solve for x. All right, so this is usually called the least squares solution because in the kind of case of the usual product on Rn or Cn, you're trying to minimize Ax minus B, which is the same thing as trying to minimize the norm squared. And if you write this out, the formula ends up being just a bunch of squares of linear functions. Okay, so that's what you're trying to minimize. Okay, so to find the solution, well, we know how to do this, right? At this point, the way that we would do it is to find an orthogonal basis for the image of A, then we can define the projection of B onto it. Okay, then that you get a vector, and then you row reduce to see what what vector of A maps onto that projection. Okay, so it turns out in this case there's actually a simpler method. So a simpler method here, which in particular involves not having to find an orthogonal basis. Okay, so to do this, note that this projection, okay, of B, or the orthogonal projection of B onto the image of A, is the unique vector in the image, okay, which satisfies B let me just call is the unique vector W, okay? B minus W is orthogonal to A for every A in the image of A, okay? In particular, this is true if and only if this vector, B minus W, is orthogonal to AK, okay, where these are the column vectors of A. Okay, and this is just because this is now a basis for the image of A. Okay, so if you're orthogonal to all of these vectors, then you're going to be orthogonal to the whole image. Okay, so for now, for every k, we get an equation. And now I'll write W as the image of some vector x. Okay, so what we're trying to solve is B minus AX, the inner product of it with AK is equal to 0. Okay, so solution to this equation is going to be the vector W that we would like. Okay, so let me just give you an example to see what's going on here, and then the general formula will make hopefully complete sense. So let's say A is going to be equal to 1, 2, 3, 4, 5, 6. Okay, so if you would like, you could think of this as a system of 3 equations with 2 variables. Okay, I haven't written down B yet, but I will soon. Okay, or you can think of it as inducing a map, say from R2 to R3. Okay, and I'm going to do the real case here. The complex case is going to be essentially the same, very small modification. Okay? And let's say I want B not in the image of A, so let's just say B is 0, 0, 1. Okay, which you can convince yourself is not in the image. So let me just draw the picture here. So here's R2 going into R3. I won't be able to do a good job of drawing this picture. Okay, but it will look like there's a plane in R3. There's a vector B not in the plane, and we're trying to find the orthogonal projection to it. Okay? And what we need to do is we need to solve, B minus AX with 1, 2, 3 is equal to 0, and B minus AX with 4, 5, 6 is equal to 0. Okay, those are the two, that's a basis for the image of A. So these are the equations that we want to solve. How do you find something orthogonal to 1, 2, 3, and 4, 5, 6? All right, so to find this orthogonal thing, right, to these 2 vectors, well, each of, the dot product with each of these 2 vectors is an equation, okay, a linear equation. And what you're exactly finding is a solution to 1, 2, 3, 4, 5, 6 of x, y, z is equal to 0, right? Now this is going from R3 to R2, if you want. And of course we know this is just the transpose of this matrix. And in some sense this is the general procedure, right? So if you want to find, so if you have this transformation, which takes these vectors, into some vector space here, you're looking at vectors in the image, okay? You want to find something orthogonal to these vectors. Writing down that system of linear equations and solving is exactly the same as writing the transpose of the original matrix and solving for 0. Oh, so I should have said this is 0, 0, 0, okay? So the same thing here works in complex case, except you have to remember that the inner product is not taking the transpose. It would be looking at for the complex, this would be looking at the conjugate transpose. Okay? But it's exactly the same procedure. Okay, and that's in general what you do. So now, of course, here for x, y, z, you're looking at b minus ax. So you want to solve, b minus ax with ak is 0 for all k. This is equivalent to solving a transpose of b minus ax is equal to 0, and again this would be conjugate transpose if you were working in the complex case. Okay, so therefore the general solution is, now you just use linearity to say this is a transpose of b is equal to a transpose a of x. So this is called the normal equation. Again, so if you're given a and b, you're solving for x, okay? And your solution here exactly minimizes the norm of ax minus b. Okay, so let's do an application of this to find best fit lines. Okay, so the idea here is we have n points in, say, R2. Okay, so I'll say they're just xi, yi, okay, from I equals 1 to n. All right, what we want is a line. So y is ax plus b is the best approximation to these points. Okay, so what does this mean? Well, we have this collection of points, xi, yi. On the other hand, I can plug all of these x values into my linear equation and get different y values. So I get yi on one hand versus the prediction, the value predicted by my formula, which would be axi plus b. Okay, so the picture is, well, I have this collection of points. Maybe that looks linear. I want to find the kind of the best line where if I plug in, so here's x1, y1, here's x1, ax1 plus b, and I want to just minimize this distance here. Okay? Oops. And of course I want to not just minimize it for one, I want to minimize it over all the points. Okay? So I want to look at the quantity, and here I guess it's more typical to minimize the square rather than the terms. Okay, so I'm looking at the sum of a plus bxi minus yi squared, and this is what I want to minimize. And the good news now is that, perhaps unsurprisingly, the framework that we've been building works, fits exactly into it, okay? So this is the same, if we wanted to actually solve this, so solving would involve finding a system, or finding a solution to the following system. So you're looking at 1, 1 here, all ones, and then x1, x2, up through x sub n, okay? And remember, these are the things that are given to you. A and B are your variables. So you're plugging this into, or you're trying to find A, B, and you want this to be equal to y1, y2, up through yn. Okay, and of course this is very, it's almost never going to be the case that you can find an exact solution, but the least squares solution here exactly minimizes the above sum. Okay. Okay, so the sum of the squares of this vertical distance is exactly the inner product of the difference of these two vectors in Rn now. Okay? So of course this is a little, it's kind of a hassle to write it down, but a computer can do this quite efficiently. So you're looking at an equation, so like kind of the normal equation now is x1 up through xn, 1 x1 up through xn of AB, AB is equal to 1 x1 up through xn, y1 up through yn. Okay, so this is something that's easy to solve. If you go online, you can just, people have multiplied these matrices together and figured out what the slope and what the y-intercept should be. Okay, so now kind of the power of this is that best fit lines was really a mirage. This thing works for best fit polynomials of any degree. Okay, so let's just say we wanted to find a best fit quadratic. Okay, well, now we know what to do, right? We would, now we're looking at, we have points, let's just say in R2, okay? y1 up through yn. We're trying to find, a plus bx plus cx squared. Okay, so we're trying to find a quadratic equation like this, which again minimizes the difference of the y values versus of the plugged in x values versus these quantities. Okay, well, now this is just solving 1x1 squared up through 1xn squared. Again, you're solving always for the coefficients, so it's a BC is equal to y1 up through yn, right? Again, you might get lucky and there's a general solution. If there's not, you just do the same general procedure. It produces for you the quadratic, which approximates these points the best, okay, up to this, squaring the difference, okay? And you can even do this in higher dimensions. Okay, so if you have, I'll just say points in R3, okay, so now we have, xi, yi, zi. Let's say we want to find a plane which best approximates Okay, so here we're thinking of z as a function of x and y, okay? So if we write, if we're looking at the equation a plus bx plus cy, this is my equation for a plane, okay? And we want to figure out, z minus zk. Well, again, it's going to be exactly the same procedure as the above. Now we're looking at x1, y1 up through 1, xn, yn, okay? And plugging in a, b, c, and we are trying to hit, z1 up through zn, okay? So there are, and of course this generalizes. You can look at points in Rn, you can start looking at higher dimensional polynomials, and you'll always essentially be looking at a similar system of linear equations and trying to minimize the area. Okay? So I think that's a good, decent point to stop. So thanks.